All right, welcome to The Explainer. Today, we're going to crack open a concept from calculus that is, and I'm not kidding, kind of the secret weapon for a huge chunk of modern economics. We're going to see how it helps businesses find that absolute sweet spot for performance. So, let's just start with a really fundamental puzzle. I mean, this is something every single company on the planet has to deal with, whether you're a tiny coffee shop or a massive tech giant. The question is simple. How do you find that perfect sweet spot where you're making the most profit possible? You know, this whole hunt for a sweet spot, well, economists have a word for it, optimization. And really, it's this universal quest. It's one of the big core problems that the entire field of economics was basically designed to solve. And the goal is always the same. You either want to maximize your profit or you want to minimize your cost. It's all about finding that one single ideal point. But how do you actually find it? Okay, so to get to that answer, economists do something really clever. They don't try to look at the whole big picture of the business all at once. Nope. Instead, they zoom way in, using this incredibly powerful way of thinking. They call it thinking at the margin. And it sounds complicated, but it's not. All it really means is asking a simple question. What happens if we make just one more item? What's the cost of that specific one? And what's the revenue we get from it? It's all about focusing on that very next tiny step. Now, this is a great idea, right? But it brings up a really tricky problem. I mean, how do you precisely measure the change that's happening in one single exact instant? If we're going to calculate the cost of that next unit with perfect pinpoint accuracy, we're going to need a special tool. And that brings us to the hero of our story today. It's a tool that comes straight out of calculus, and it's all about measuring the slope, not of a whole line, but of one single fleeting moment. And that amazing tool is called the derivative. Its whole job is to calculate the instantaneous rate of change. Okay, that sounds a little technical, but what it really means is it tells you exactly how steep a curve is at one specific point. It perfectly captures that idea of a marginal change we were just talking about. And you can picture this. It's actually pretty cool. Geometrically, the derivative is just the slope of the tangent line. And a tangent line is just a straight line that kind of skims the curve at a single point. It just kisses it. It shows you the exact direction the curve is pointing in right at that very instant. Okay, but here's the thing. There's a catch. This super powerful tool, the derivative, it has one critical rule. One condition that is absolutely non-negotiable for it to even work. For a derivative to exist, the function has to be what we call differentiable. And at its heart, all that means is that the function has to be smooth. Seriously, think of it like a perfectly paved road. No potholes, no sudden breaks, and for sure, no sharp, jagged corners. This is a perfect way to see what I'm talking about. On the left, you've got this nice, smooth ride, a predictable, well-defined slope at every single point. But then, look at the right, a sharp corner. That V-shape is a classic example. It's from an absolute value function. Right at that pointy bottom, what's the slope? Is it this way or that way? You can't draw a single unique tangent line, so the slope is undefined. The derivative just, poof, doesn't exist there. So here's the bottom line. Any of these weird features will break our tool. A sharp corner like we just saw? Nope. A spot where the line goes perfectly vertical? Can't do it. Or a place where there's a break or a jump in the graph? Forget it. At any of those spots, you can't define a single unique slope, and that means the function is not differentiable there. And this leads us to a really important idea in calculus. It's a bit of a mantra. Every differentiable function is continuous, but not every continuous function is differentiable. What does that mean? Well, to be smooth, a function has to at least be connected, or what we call continuous. But just being connected isn't good enough. Think back to that V-shape. It's totally continuous, you can draw it without lifting your pen. But that sharp corner means it's not smooth. So smoothness is a much stricter condition. Okay, let's bring this all the way back to our original economic puzzle. Now that we have this amazing tool, let's see how it helps us solve the problem and actually find that sweet spot. And you know what? It's basically a three-step recipe. It's actually pretty straightforward. Step 1, you model an economic concept, like, say, your total cost, with a nice, smooth function. Step 2, you take its derivative, and that gives you the marginal value, the cost of making just one more. And then step 3, you use that marginal value to find the optimal point. That's it. Think about marginal cost, or MC. It's a term you hear thrown around in business all the time, right? Well, it's literally nothing more than the derivative of the total cost function. It's the perfect, precise mathematical way of thinking at the margin. And here is the big payoff, the solution. The absolute maximum profit is found right at the very peak of the profit function, where the slope goes completely flat. It's zero. And our awesome derivative tool tells us that this happens exactly when the money you make from that next item, the marginal revenue, is perfectly equal to what it costs to make that next item, the marginal cost. That's it. That is the economic sweet spot we've been looking for. So let's just quickly recap the key distinctions here. Continuous just means connected, no breaks or jumps. You can draw it without lifting your pen. But differentiable means it's smooth, no corners, no breaks. It's that special property of smoothness that unlocks this entire powerful method for finding the best possible outcome. And that leaves us with one last kinda provocative thought. If all of our elegant economic models are built on these nice, smooth functions, what happens to the economy when we hit a sharp, unpredictable corner in the real world? What happens when we hit a financial crisis or a global pandemic? What can our toolkit tell us then? It's definitely something to think about.